Good day, ladies and gentlemen, and yeah, it's been a while since we last met one another, and it's good to have you back as we are preparing for the exams. I know most of you are writing your exams, and we are busy working hard, trying to make sure that we do well for those exams. All right, so today I'm going to be just looking at physical science, the 2021 paper that was written in May, June. I thought it was really quite an interesting paper to look at as we prepare for our final exam, um, which will be written very soon. So if you haven't subscribed, yeah, please be part of the family. Otherwise, please make sure that for those of you who have challenges with mathematics or physical science, you're more than welcome to get in touch with us. And our email address is info@mlungisinkosi.co.za. All right, shall we get into it as we gather strength again, to prepare for the exam. So I'm starting with the multiple choice section, and in this case, we're just going to be looking at obviously all the other questions as we've been doing. I'll be posting fresh questions each day, perhaps several per day, just to help you prepare rather for that final exam. All right, let's look at the first question. And the first question says, we've got a constant net force that acts on a body moving in a straight line. Which one of the following quantities associated with the object will remain constant during the motion? All right, and this reminds us of Newton's second law, doesn't it? Because we know when we've got a constant net force, what does it mean? It means that we've got a constant acceleration as well. So in that case, our correct answer would be C. Now, just to talk about the others, why wouldn't they be correct? Remember that an acceleration, or a net force, by the way, causes an acceleration. And what is acceleration? It's a change in velocity, right? Now, the moment you change velocity, it means that you'll change momentum, which is dependent on velocity. It would mean that the kinetic energy also changes. So in that case, it means that the most correct answer, or rather the correct answer for this question, 1.1, that should be C. Right, as we look at question 1.2, they say the weight of an object on the surface of the earth is W, right? Now remember, in this case, we know that the weight is actually due to the force that the earth exerts on an object. The force, the earth attracts the object towards its center. So that is what we call gravitational force, or in this case, the weight. They say, what will be the weight of the object on the surface of another planet of the same mass as that of the Earth, but twice the radius of the Earth? Now, what I'm going to do is I'm just going to sort of break the weight into a mathematical equation so that I show you how we get to that. Now, if we think about weight, as I had said, we know that weight, or the force of gravity in this case, it's going to be gravitational. This is what we call the universal gravitational constant, multiplied by the mass of the earth and the mass of the object, whatever that object is, divided by the radius of the earth. Now let's call the radius of the earth RE, right? So that's divided by RE squared. So what's going to happen? So in this case, if I take that same object, remember the mass of the object remains constant, right? They did say the planet has got the same mass as that of the Earth. So let's call it planet X. So let's say the weight on planet X would now be equal to G. That would be the same mass as the mass of the Earth. So I know that's mass of planet X, but remember it's the same as the mass of the Earth, right? Multiplied by the mass of the object. Remember, it still remains the same, but now they told us that the radius is twice the radius of the earth. So in this case, it means that it's 2re, okay, squared. So in this case, what does it do? We've got gme, the mass of the object, that's 4 times RE squared. Now in this case, what we want to do is to relate this weight on planet X. We want to relate it to the weight on the Earth, right? So what we're going to simply do is, okay, so let's perhaps multiply the bottom by 4, by 1 over 4 rather, the inverse, so that we remove that 4 at the bottom. But remember, what I do at the top, at the bottom, I need to do at the top. So in this case, what does that give me? 1 over 4, can you see, I'm now going to be left with GMEMO divided by RE squared. So in that case, it means that the weight on planet X would be a quarter of the weight on planet Earth, right? So it should be 1 over 4 W. So in this case, it means that the answer to 1.2 is A. I hope that helps in being able to answer these type of questions. All right, as we swiftly move along, right, let's go to the next one. So they say to us, they say which one of the following statements correctly explains why the cricket player moves his hands downwards. Okay, so if you think about it, a cricket player doesn't just put their hands, stiffly, okay, as they catch a ball, but they actually kind of move them downwards, right? In this case, they say, why does the cricket player move the hands downwards? So the first, response there, they say the impulse on the ball is decreased. In fact, you know what we should do? Rather, let's look at, so this is related to the impulse momentum equation. Remember that in this case, when we talk about the impulse momentum equation, we say, well, this is the change in time equals to the change in momentum. So when the cricket player receives the ball, so I want you to note, if he kept his hand, or she kept her hands, stiff in the air, what it would do is that it causes the change of momentum to occur very quickly. So that time there is short, and when that time is short, okay, for the ball to change momentum, come from a high velocity, in this case to stop, in this case what happens is that it causes that force. So when the time is less, the force of impact is much. Okay, so if you think about it, so what would the cricket player want to do? He'd want to actually extend the time or prolong the time that it takes to change that momentum. And so what that does is that it will actually reduce the force of impact. So in that case, I think the most correct answer when I look at that is D, because it says that the time it takes to change the momentum of the ball is increased, as we've just said. We increase the time it takes, and in that case, what does it do? It will decrease the force of impact. Okay, so our correct answer there on 1.3 should be D. Okay, right, as we move swiftly along. Okay, question 1.4 quickly. They say, consider the motion of a small stone that's thrown vertically upwards until it reaches its maximum height. So obviously, as it goes up, it means that the velocity will keep decreasing, right? They say ignore the effects of friction. Okay, so we know that it's moving under projectile motion, so it means that in that case, gravity is the only force that's acting on it. So they say, which one of the following combinations of graphs correctly shows how the momentum and the gravitational potential energy of the stone change with time? Now, when I look at those graphs, now I'm just going to move that. When I look at those graphs, now if you think about it, the momentum, if you think about gravity, or rather its change in height, as it goes up, the velocity decreases, and it will get to that point where it actually stops when it gets to maximum height, right? So in this case, when I look at that, okay, going to say, well, there's a constant change in velocity. Now, if you think about it, acceleration is constant. So what that means is that there's a constant change in velocity, right? In this case, when I look at the graph that shows me a constant change in velocity or change in momentum, in that case, I'd say the two options are between B and D. All right, but now let's talk about gravitational potential energy. So what happens to the height with time? So if you think about, equations of motion, okay? So if I think about delta y is equals to vi delta t plus 1 over 2 a delta t squared. So if you look at the relationship between displacement and time in that case, you can see that that relationship is actually a quadratic, it's a quadratic relationship. So in this case, that means that if I think about potential energy with time, remember that potential energy is related to that height there. So with time, in that case, it would mean that that graph would be a somewhat of a parabola, right? But if you think about it, what's happening to the height? Okay, so that height is changing with time. Okay, so in that case, I look at those two graphs. Okay, so we said the option is between B and D, and the one that shows us a parabola for the change in displacement, or in potential energy, is D. So in that case, for 1.4, I'd consider option D. Okay, right, I hope that makes sense. So that's option D. Need to write that down there. Okay, right, so as we go along to the next question. All right, question 1.5, they say a boy and a girl have different masses. Please note that. They say they are initially addressed at point P. They slide down different parts of a water slide as shown in the diagram below. Ignore the effects of friction. So remember, there's no frictional force in that case. They say consider the statements below regarding the boy and the girl, right? So let's look at the statements. They say, first of all, we've got, they say only conservative forces act on both the boy and the girl while they are sliding downwards. Okay, so if I look at that, there's no frictional force there, which is a non-conservative force. There's no applied force there. So there's nothing pushing or pulling the boy and the girl except, for our conservative forces, which is the force of gravity in that case. So as a result, I would regard that statement as being correct. Okay, so statement 1, I would say that's correct. And then they say the boy and the girl each each have the same gravitational potential energy at point P. Remember, their masses are not the same. Much as the height is the same there, but their mass is not the same. So therefore, the gravitational potential energy cannot be the same because it is dependent on mass after all. And option 3, they say on reaching point Q, the speed of both, of the girl is equal to that of the boy. I think that would be correct. Now, if you think about it, I'm just going to just move this here. If you think about it, so if you say mechanical energy is conserved between point P and point Q, so what is mechanical energy? We know if mechanical energy at P is equals to mechanical energy at Q. And by the way, I could use this theory because in this case, there is no frictional force and there's no applied force. There's actually just conservative forces, right? So if you think about potential energy at P and kinetic energy at P, it would be equal to potential energy at Q, so EP plus EK at Q. But then what do you notice? You'd notice that potential at P, they will have no kinetic energy, and at Q, they would have no potential energy. So it means that EP at P should be equal to EK at Q, right? Now, if we were to try and express them, so we know this would be mgh, okay, for either one of them, by the way. I'm deriving this for either one of them. This would be, sorry, half mv squared at Q, right? But notice what you can do. You can actually just divide by the mass, so that ultimately when I solve that, V is actually equal to the square root of 2gh. You can work it out and see that you get that. So that's the square root of V. If I multiply by 2 on both sides, that gets rid of that half. I've got 2gh on that side, and when I take the square root, I'm left with 2gh. Now in this case, the height is the same, gravitational potential energy, gravitational acceleration rather, is the same. So as a result, it means that their velocities should be the same. So to answer that question, yes, absolutely, it would mean that 3 is actually correct. So in that case, I'm going to choose option B, which says option 1 and 3. Right, I hope that makes absolute sense as we continue with this question. For the sake of space, I'm just going to continue over the other side. So they say an astronomer observes that the light of a star, that the light spectrum rather of a star has been blue shifted. So remember, the moment that we have a blue shift, what it suggests to us is that, whatever object or whatever planet or star rather is moving towards the Earth, right? So in that case, it would mean that obviously the frequencies are moving more towards the blue end. The spectral lines rather are moving towards the blue end, and that's how we are able to conclude that it's moving towards the Earth. So they say, how have the observed frequency of the light from the star and the distance between the star and the Earth changed, right? So remember, the observed frequency is shifting towards the blue end, right? So in that case, it would mean that the observed frequency has increased. Remember that when you think about Roy-G-Biv, right? So if I were to write that down there, okay, let's bring it down a bit. So Roy-G-Biv, if I were to write that like that, remember that red has got the lowest frequency, it's got the longest wavelength, but it's got the lowest frequency. So as I move towards that direction, towards the blue end of the spectrum, then I know that frequency is actually increasing. All right, so in that case, it means that the observed frequency is increasing. Okay, it has increased. And then the distance between the Earth, the star, and the Earth has decreased. Of course, if it's moving towards the Earth, it means that the distance between the star and the Earth is actually decreasing. So the correct answer there, okay, so I'm going to say, so for 1.6, we're going to actually consider B as our final answer. All right, then the next question, 1.7, they say a small negative point charge Q, right, is situated halfway between two identical spheres. P and Q carry identical charges, as shown below. Right, now they say sphere P exerts an electrostatic force of magnitude F, all right, on sphere Q. What should the magnitude of the net electrostatic force experienced by the point charge, what should it be? Okay, I would consider my option to be 0 there. And I mean, if you think about it, that point charge there experiences a force because of Q, and it also experiences a force due to P. But remember, P and Q have equal charges, identical charges, right? And that would mean, if, just for argument's sake, if P is negative, just for argument's sake, or positive for that matter, because they said it's a negative charge here. So if we know that P is positive, then it means it's attracting that small charge Q there towards itself. But it means that Q is also, big Q rather, is also attracting small q towards itself with the same magnitude of force in that case. So it would mean that the net force that it will experience would actually be zero, because it would have two forces that are actually opposing one another. So I would say, well, the option there should be option A, which is 0. Right, hope that makes sense. Okay, next question, 1.8. They say, consider the statement below regarding AC and DC power. They say AC voltage can be changed during AC power transmission. Okay, so that would be true. Remember that we can always change AC during power transmission. Yeah, we can always obviously use our either step down or step up transformer to do that. Right, and then the second one, they say DC power transmission requires transformers. That is not true. Remember, only AC can be changed, right? And then in that case, they say AC power transmission is more efficient. That is absolutely true. Okay, so in that case, the two correct answers there would be 1 and 3. So that would be option C. Okay, please just remember those advantages between AC and DC. And in that case, remember that it can always be transformed, and it's more energy efficient, and it is also more environmentally friendly to use AC power. Right, let's go to 1.9 quickly. They say in the circuit diagram below, all resistors are identical. Ignore the internal resistance of the cell and the resistance of the connecting wires. Okay, so they say when switch S is closed. Now note, in this case, when switch S is closed, we know that there's going to be current that is moving. Now you note there, you'll have current moving into resistor R. You'll have another current moving through this other resistor. So the one that was here breaks down again into, or rather divides. Okay, so in that case, we know that there'll be, those two are in parallel with each other, right? And the combination of them should be in series with this resistor here. The combination of all of these should be in parallel with that one resistor R there. Now they say when switch S is closed, the reading on voltmeter V1 is 3 volts. Okay, what will be the reading on voltmeter V2? So what I want us to do is just to consider this question quickly. So what's happening there is that, let me just draw these two resistors. When we take the parallel combination of those two resistors, what we actually will end up getting there is that the effective parallel resistance of those two will be a half of R, and obviously this one will remain as R, the one next to it, right? But remember, these two are in parallel with this one resistor R, that we were told that the voltage across this one R is actually 3 volts. Now, if you think about resistors in parallel, we said parallel resistors, the voltage is the same. So the voltage across these two should also be 3 volts, okay? Because that's in parallel with that. Now, what do we know about resistors in series? Resistors in series divide voltage, okay? But now, how do they divide voltage? They divide it proportionally. So because that's a half of R and that's R, it means that the voltage here should be twice the voltage there. Now remember, they are sharing 3 volts, right? So if you think about it, in that case, it would mean that this one will take 1 volt, and twice of that would be 2 volts, because you've got this resistor here being twice that value there. So you've got 2 volts here and 1 volt there, 1 volt there, so that the combination of all of them should be 3 volts and should be the same as that one. So as a result, it would mean that the correct answer, they say what will be the reading on the voltmeter V2. So V2 should actually be 2 volts. Okay, so in that case, it means that we are going to take option C. All right, hope that makes sense. If you wanted to look at it mathematically as well, you know, there's an equation, a formula that you can use for resistors in series when you want to see the voltage division. So I could say, well, what is the voltage V1? V1. So the voltage V1 would actually be, so you take the resistance that it is measuring across, so it's resistor R, divided by the sum of the resistors. So in that case, you'd have a half of R plus R, which is 1.5. Okay, so 1 plus 1.5, 1 plus a half, that should be 1.5 of R. Okay, so that's the combination of the two multiplied by the total voltage. Okay, so you always say it's the resistor multiplied by the sum of them divided by multiplied by the voltage across all those resistors. So what you'd notice, that and that goes away, so 3 divided by 1.5, that should give you 2 volts, and that's the voltage across V2. Okay, so I hope that makes sense. Right, let's go to the next question. Sorry about that, I didn't show you the rest of the options there. All right, so we took the option C, which is 2 volts. Right, as we move on again to the next question. Right, and the last question, it says some of the energy levels of an atom are represented in the diagram below. Now, just to explain this just a little bit, so because they're showing us the energy levels of an of an atom rather, I want you to please note that, you know, when you've got those energy levels obviously moving from an excited stage, okay, so we call that the excited state in that case, and they drop below, right, and they drop to the ground state, or it shows a loss in energy. What we would then remember, energy cannot be created or destroyed, but it's transformed, right, from one form to another. So what you would observe is a line emission spectrum. So it means that energy would actually be displayed as in the form of light. Okay, but in this case, now to move it from the ground state to the excited state, it means that it would actually have to absorb, get energy, right? So they say which one of they say E0 rather represents the ground energy state energy. They say which one of the energy transitions below represents the absorption of light. Note, they say the absorption of light of the lowest frequency. Now, I want you to please note, if we take light of the lowest frequency, in that case, remember that frequency is related to the energy of light, isn't it? So in that case, it means the lower the frequency, the lower the energy transition will be, right? So if I look at that, the options that I have, E0 to E4, that's quite a big jump, isn't it? E1 to E3, okay, it's 2 energy levels up. E3 to E4, can you see it's only 1 energy level up, right? So in that case, I would say, well, that would be the one, and that's E3 to E4. However, ladies and gents, I want you to please be careful because sometimes they ask us about wavelength. Remember, if we were to consider wavelength, the lower the energy jump, okay, in that case, it would mean the longer the wavelength of that light would be, right? Because remember that energy, if you were to write that equation, that's hc over lambda, right? So it would mean that if I were to have a lower energy, it would mean that would be the highest wavelength. Okay, so just keep in mind of that inverse relation there. So however, to answer this question, it would mean that we would consider that that option, E3 to E4. All right, I think I want to leave it here. Of course, we'll be looking at some more questions going forward. I hope you will enjoy this question paper as we'll be looking at it in the coming days. Please don't hesitate if you have some questions or if you need assistance as you prepare towards your exams. Please don't forget to send us that email. That's info@mlungisinkosi.co.za. But otherwise, please just make sure that you keep following us on the coming days. Thank you. I'll see you next time, ladies and gents. Sharp, sharp.